Problem 17 says Susie flips a fair coin 6 times. So we want the probability that Susie flips 3 heads in a row, but not 4 heads in a row. What's the probability that Susie flips 3 heads in a row, but not 4 heads in a row? So you're saying you want to find the number of ways to get 3 in a row and then the number of ways to get 4 in a row? Are you saying we're going to find the number of ways to get at least 3 in a row, or the number of ways to get exactly 3 in a row? So what exactly do you mean? Okay, exactly 3 in a row. But the thing is, if we get exactly 3 and we find the ways to get exactly 3 in a row, is it possible to get 4 in a row? If you have 3 in a row, that means it's surrounded by 2 heads, 2 tails. So if it's surrounded by 2 tails, is it possible for there to be 4 in a row? No, it's not possible. If we have 3 heads in a row, exactly 3 heads in a row, then there's no way to get 4 heads in a row. So we can just do casework on the 3 heads in a row and not worry about anything else. Also, we never double count because think about this. If we double counted, we have to have 3 heads in a row here and then 3 heads in a row here. That's the only way for us to double count. Because if we had 3 heads in a row anywhere else, then there wouldn't be place to put another 3 heads in a row. So basically, we only have this option for overcounting, and this gives us 6 heads in a row. So if this is 6 heads in a row, then it's not 3 heads in a row anymore. It's just 6 heads in a row. So this case doesn't even work. Therefore, there's no overcounting we even have to worry about. We can just do casework on where the 3 heads are. Okay, so you're saying we do 6 choose 3 times 2 to the third minus 1. Okay, there are some problems with this. First of all, why do we need to do 6 choose 3? Let's say we pick here. Let's say we have 6. So you said we want to do 6 choose 3. But what if you pick this, this, and this, for example? And you say, these are my 3 heads in a row. Well, you can see the problem with this, right? They're not in a row. Okay, so now our new answer is 4 factorial. I'm assuming that's because you have the heads, 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 head, so then you're trying to group these together. And then the other ones are just, you can do whatever, right? But here's the problem with this. Let's say there are 4 options of where to place this block of heads. Let's say we just have these heads. But let's say the next flip is tails. So then this is fine, right? But let's say we have 3 heads, and then we pick the next flip, and then it's heads again. The problem is that we can't let the other ones be anything they want to be, because we want exactly 3. We want exactly 3. So then it's just not going to cut it. We just can't do that. So here's the thing. We have to do casework on where the heads are, because it really depends. For example, if we have heads on the edge here, then the next one has to be tails, because we're going for exactly 3. And then, however, these two can be anything they want. But let's say we have heads in the middle. Then this block of heads has to be surrounded by tails. That means we only have 1 one flip that we can choose to be whatever it wants. So this means that not all cases here are created equal, so some of the cases are going to be different than others. That means we have to do casework on each individual placement of the heads. So let's start with 3 heads here. So how many ways are there to choose this one? You're saying it could be heads or tails? We have 3 heads, and then, okay, yeah. Okay, let me just re-explain it then. So we're trying to do casework on each individual placement of the heads. So first, we're going to do the case of when the heads are the first 3 flips. So we want to know after these first 3 flips, how many ways are there to choose the next flip? We're going to find the number of desirable outcomes over total outcomes, because each outcome is equally likely. So we want to know if we have 3 heads in a row, then how many ways are there to choose the next flip? We only have one choice. It has to be a tails. The reason why is because if it were heads, then that means this streak would be 4 heads in a row. And the question literally tells us not 4 heads in a row. So there's only one option, and that's tails. How about the next one? How many options are there for the next one? Yeah, 2 and 2. Because the reason is that we don't care if it's in heads anymore, because there's no way to get another streak of 4 heads in a row. Because we already have 4 here, and there are only 2 more spots. So we don't really care what they're going to be, because it doesn't matter to us. So that's 4. So then how about if the heads are here? How many ways are there to choose the first one? We know that we can only have, yeah, exactly. There's only one way. Because, or else it would be 4 heads in a row. How about this one? It's also 1, yeah. Because if we had here, this would be 4, and the next one is 2. So then there are 2. Now look here. It looks like we have to do it again for 2 more cases. But the thing is that this is symmetrically equivalent to this. If we flip it around, then it's the same thing. So that means if we have all of them, if we reverse this, and there are 3 heads in a row but not 4 heads in a row, there's still going to be 3 heads in a row but not 4 heads in a row when we flip it around. So that means the number of ways that satisfy this with heads here is equal to the number of ways that satisfy it here, because of symmetry. So then this one is also 2, and the next one is also going to be 4, because it's symmetric to the first case. So now the total number is 4 plus 4 plus 2 plus 2 equals 12. And then how many total possibilities are there? How many total? If we flip 6 coins, how many total possibilities are there? 2 to the 6th. And that's 12 over 64. So the answer is 3 over 16. So we want this. It's 19. So the answer to this question is 19.